Hello students, welcome to lecture number 14 of computer architecture course. So far till the medsim we have learned about the basics of memory, and we've also seen about the data path architecture of the MIPS processor. In the basics of memory you have learned about the different technologies that exist for DRAM architectures, starting from SDRAM and SDR, SDRAM and so on and so forth, DDR, SDRAM. You've seen the difference in terms of the performance metrics like burst rate and peak bandwidth and so on. So now, since we have covered till the midsem about all the basics of memory, especially in the context of the current technologies that exist for different DRAMs in the market, now let us move a little bit inside the memory architecture, and of course then we will gradually get into the cache portion of the computer processor. So in today's lecture we will focus on the memory hierarchy a little bit, and I will also talk about the basics of the memory blocks and giving you the concept of why memory is important, and then we'll go into the details. Okay, so let's get started. So what is a memory hierarchy? So this is a very popular word that is often used in the industry to enhance the performance. That okay, we can deploy memory hierarchy to enhance the performance. That is very crucial, and I've seen it that people often use it in the language which many people don't understand. So it's important to understand what exactly memory hierarchy means. So first of all, it is used to improve performance by introducing the cache memory between the microprocessor and the main memory. So these two are very important keywords, that we have at one end the microprocessor and we have the main memory at the other end, and we will introduce cache in between that. Okay, so that is the main step of performing or designing memory hierarchy based systems. And this cache is basically formed by a small amount of faster and expensive SRAM. I believe I have given you the basic difference between SRAM and DRAM already. So it is important to note that cache is basically formed by a small amount of faster and expensive SRAM. How does it help? It helps in providing acceleration to the execution process. Thereby, it helps in assisting the memory access of the slower and cheaper DRAM. Okay, that's how the smaller and faster SRAM, known as cache, is actually useful. Over the period of time in the evolution of memory industry, caches have really become multi-level. Okay, so we really don't use a single level cache now. It has become a multi-level cache, and this multi-level memory that comprises of the cache memory, okay, that could be multi-level or single level. The smallest of the memory components, which are known as registers, the RAMs, and the secondary storage, which is the hard disk that I'm referring to, collectively they form as memory hierarchy. So if you look into this diagram, you will see registers are right on the top of the pyramid, followed by L1 cache, that is level 1 cache, followed by level 2 cache, then you have the RAM, and finally you have the secondary memory. So this RAM that I'm referring to is basically DRAM. Okay, so now you already know what DRAM is. So this is basically DRAM. If you want to really have a faster memory, this will be actually DDR DRAM. Okay, and if you see that on the top of the pyramid, the speed is the highest, and as you come below the pyramid, the speed becomes slowest. So highest is for the registers and slowest is for the secondary memory. And in the context of cost, which is the design cost, that is a measure or function of the hardware chip area that is used to design each of these blocks, the cost is the highest because it is very expensive to design caches and registers, and as you come below, the cost becomes lesser and lesser, okay, till you go to the secondary memory. Of course, if you see the size, that is the third parameter. The size again the largest at the lowest level and smallest at the highest level. Now another representation of memory hierarchy is as follows. It could be in terms of the storage capability and delay. So you have the CPU register right on the top of the pyramid, followed by CPU caches, which are L1, L2 and L3. Then you have the main memory, which is DDR1, 2, 3, DRAMs and so on, and you have the permanent storage, which are known as SSD and HDD, hard disk drive and secondary storage drive. These are also known as persistent storage. So in terms of the storage capability, the CPU registers have storage in the order of few KBs. The CPU caches have storage in the order of few KBs to MBs. The main memory has storage in the order of few GBs to TBs, which is gigabyte to terabyte, and the persistent or the permanent storage has storage in the order of more than or in the excess of TBs. Okay. On the contrary, for delay, of course the delay is going to be the lowest for CPU register, because that is the fastest component in the pyramid, and the persistent storage has the highest delay because it is the slowest of the lot. Now if you see this diagram, we have an interconnection of the CPU registers followed by caches, one or more levels. Then you have a main memory, and then you have a disk storage. So in between the CPU registers and the caches, which have one or more levels, you have a specialized bus. Okay, that could be internal or external to CPU, but that is a specialized bus that carries the information between register and the caches, or you can say that is responsible for connecting or communicating between the two components of the memory hierarchy. Then you have a memory bus, which is connecting the cache and the main memory. So main memory is the DRAM that we are referring to, and then you finally have an IO bus, input output bus, which is actually communicating between the disk storage and the main memory. So you can see that in the memory hierarchy, we basically have a trade-off between size, speed, cost. Okay, if you recall the first pyramid that I've spoken of. So these are the three most important parameters in the context of memory hierarchy. It's a trade-off between size, speed and cost, and it exploits the principle of locality. Okay, we'll come to this a little bit later, but there's an important property known as principle of locality. So we'll specifically see this when we go to the lecture on cache memory. Okay, but as of now, just keep this word in mind that this is an important property besides the trade-offs that I'm talking about. In case of the registers, the fastest memory element it is, and it is the smallest storage, very expensive. You know how to design registers. We had already learned about it in the logic design course. Okay, that how we can make a bidirectional shift register that can operate in one of the four modes, PISO, SIPO and so on. So that's what registers are. These are made up of sequential elements like flip-flops. And then we have the cache, which is the fast and small form of the main memory, or the smallest form of memory compared to the main memory, which is DRAM, and it acts as a buffer between the CPU and the main memory, and it records or contains the most recently used memory locations. Okay, so here where the address and the content both are recorded in the cache, the most recently used memory location. Okay, that is the most important thing here. The main memory is the RAM of the system, which is often used in the parlance of memory we often call of RAM. So this is the RAM, the main memory, and finally we have the disk storage, which is the permanent memory. Now in this slide, let me talk a little bit about the different properties or characteristics of memory in the context of category, erasure technology, write mechanism and volatility. These are the four different properties. What type of category of memory we are referring to, what is the erasure mechanism, what is the write mechanism, and whether it is volatile or not. So RAM, which is random access memory, the category is read write, both is possible. Erasure technology is electrical, that is we can electrically erase the contents of the memory. Write mechanism, we can of course write also using electrical procedure, and it's a volatile form of memory. The next is ROM, read only memory. Here the category is only read, we cannot write, because writing is only done at the time of manufacturing, we cannot write later. So erasure is therefore not possible because it's permanently there inside the ROM. We can write using a process known as masking, which is used mostly when we do the perform the manufacturing of the ROM, and it's a non-volatile memory. Similarly, for programmable ROM, which is another type of ROM, it's read-only, erasure is not possible. The writing is slightly different. We can do using electrical mechanisms, and it's again non-volatile. And erasable PROM is known as EPROM. So I remember I had used an EPROM in one of my research projects when I was in Canada, and this electrically erasable or simply erasable PROMs or EPROMs, one of the examples is GAL 16V8 or PAL 16V8 chips. You can look into that in the internet. So these type of chips are very popularly used for erasable PROMs. Again, I'm referring the name. It's called GAL 16V8 or simply PAL 16V8. So the important property of this is that this is again read only. You cannot write it, but you can erase it. Okay, you can erase it not simply by electrical process, but you have to put it inside a UV box, ultraviolet box, and keep it there for 15 to 20 minutes until it takes time to completely erase all the data inside it. And then again we can programmatically write it using some PAL language. Okay, it's a programming language that is used to program a PAL chip or a GAL chip, which is EPROM basically. So that's what I'm saying. Writing mechanism is electrical and it's non-volatile. Simply same thing for electrically erasable PROMs. And finally we have the flash memory, which is again read only, and it is again erasure is electrical and it's again non-volatile by nature. So in this slide you've seen there are different types of memory. Specifically there are 6 different types of memory. Okay, broadly speaking the memories are RAM, ROM and flash. Simple. Okay, so these are the 3 different types of categories of memory available in the market. In case of RAM, which is DRAM, I think I have already spoken a little bit, but let me tell it once again. Initially the data is stored in the DRAM chip, and the charging of its memory cells to the maximum value is performed, and as we know the charge slowly leaks out and eventually would go to a low value to represent valid data. Now before this slow leakage process happens, we have a refresh circuitry that reads the content of the DRAM and again rewrites the same data back to its original location. Therefore we can restore the memory cells to its original maximum charge or original value. So that's how DRAM works. There's a refreshing happening, for example 100 plus times per second, okay, in order to keep the value intact. On the other hand, for SRAMs it is similar to register. So once the data has been written, it will stay valid and it need not be refreshed. And therefore static RAMs are again faster than DRAMs, as well as therefore more expensive. And caches in PCs are made up of SRAMs, as you know. So ROM, it's a permanent storage. The applicability of ROMs are for microprogramming. For library, we can store library subroutines because we don't want it to be erased. Constant data, system programs like BIOS for personal computers or applications, or the operating system for certain embedded systems are also programmed inside ROM so that it remains permanent. And as I said, the writing of the data, whether it's an OS or BIOS or library subroutine, whatever it is microprogrammed during manufacturing process, or it could be programmable, using special equipment, because we need programming softwares and programming kits to program information into the PROM, and it is erasable only by ultraviolet radiation. As I said, for example, GAL 16V8 chips, you can look for it in the internet to get more information, and therefore it takes much longer to write than read. Okay, so writing process takes time. So this is the different type of ROM that we are referring to, and this is the internal structure of ROM. You have a decoder for feeding the address. Okay, we have a 6 to 64 decoder, and once the output of the decoder gets into the OR gate array, then it could generate 64 times 4 different available options, because we have 4 different OR gates. So in total we have 64 into 4, 256 fuses that are of 256 wires that are connecting. So these are all interconnected into the decoder. Okay, so that is where we actually could read the data from, okay, once it is written during the manufacturing process or through microprogramming. Now let me talk a little bit about the memory analysis. So we have two different types of memory components. One is known as on-chip memory and second is known as off-chip memory. It is often a myth that people believe that memory is always not inside a processor. The processor can also contain the memory, as in like if it is all both placed on within a single chip platform. So that's why these are known as on-chip memory components, because they are within the processor on a single fabricated platform, and these memories are registers and L1 cache. So only these two are allowed to be on chip, while the rest of it like L2 cache, L3 cache, the main memory like SDRAM and the permanent storage like HDD, they are always off chip. Okay, because of two reasons. First is because of the size and second is the cost, fabrication cost, and the size of the chip is definitely larger than L1 and register. Performance analysis, the average memory access time is given by a function which is a combination of the hit time, which is the time taken to determine if it's a hit, that is cache hit basically we are referring to. So the time taken by the algorithm to determine if it's a cache hit, so that is the time for hit time, plus we check the miss rate, that how often we have a miss, multiplied by the miss penalty time, that is in order to determine whether it's a hit or a miss is referred to as miss penalty time. So that multiplied by the miss rate gives you the total time for the misses plus the hit time. So that is average memory access time. Now there are a number of ways through which we can improve the performance of caches. So besides implementing effective memory hierarchy, which you have already seen, some further additional techniques can also be used to enhance performance. The first is known as reducing miss rate. You can reduce the miss rate by increasing the dimensions of the cache and their blocks. Okay. Second is having something known as higher associativity. We will specifically put this explanation on hold for a while, because we will talk about it when we go into the cache memory lecture. And then we have hardware prefetching mechanism. So I'll talk a little bit about it in this lecture itself, what is hardware prefetching. So these three techniques like hardware prefetching, having higher associativity for caches, as well as increasing the dimensions of the cache and their blocks, would reduce the miss rate. So this is one of the first ways to reduce miss rate. The second is known as reducing miss penalty. Reducing miss penalty can be done by using multi-level caches and also by giving priority of reading over writing when you have a miss. And third is reducing hit time. This can again be accomplished by having simple small caches. Now let me talk a little bit about what is prefetching, because prefetching plays an important role in reducing the miss time or miss penalty. So prefetching is a process of fetching data closer to the process before it is needed. Okay, as we can fetch the data in advance closer to the processor and closer to the process before it is needed. So there is some sort of prediction that happens here. So the essence is, the goal is that the data will be ready in advance and available when the processor requests for it. So even before the processor would request, the data will be kept ready and made available as soon as the processor would place a request for it to the memory. Without prefetching, the processor may have to stall and wait for the data to come in if we have a bandwidth limitation, or in case the memory access time is more than the processor would have to wait. And the prefetching can again be applied at different levels. So there could be disk to DRAM prefetching, or there could be DRAM to cache prefetching. Okay. In this context, we are mostly talking about DRAM to cache prefetching and not to disk to DRAM hardware prefetching mechanism. So prefetching to caches, which is the DRAM to cache prefetching, is done through something known as hardware prefetcher. And this block's main job is to eavesdrop on the memory accesses going on from the processor to the caches, and it keeps on monitoring that whenever any memory locations are being accessed by the processor currently, is there a particular pattern involved in that. So basically it keeps on monitoring the memory locations being accessed by the processor and predicts through those patterns in case which locations could be again useful in the future. Okay. So that is a prediction mechanism which I was talking about. So that's how the prefetching from those memory locations are already made in advance to to the processor before they are used or before they are made a request for. So some example could be that, for example, prediction is tough, but it is useful when you have a constant stride pattern. That is, whenever we know that okay, in a particular gap of certain intervals the memory locations are being continuously used, or we have a specific pattern in the accessing of the memory locations, so we call those as detecting constant strides, because it's a constant stride of say 4 bytes or 8 bytes, so we will keep accessing those memory locations. So therefore prefetcher are not good at predicting random access. In case a program jumps all over the memory, or it follows links which are scattered all over the memory, then prefetcher does not become useful, because then there is no pattern. So therefore hardware prefetcher is only useful when a program is having some pattern, or it is going through a process of constant strides. Then the hardware prefetcher will eavesdrop the memory accesses and will predict the locations, okay, that this location could be again useful in the future based on whatever has happened in the past. So it keeps a track of the history of memory locations being accessed. So through this mechanism of hardware prefetching, the cache performance could again be improved. Okay, so we are done with the basics of caches and basics of memory and the technology of memory in the past lecture. In the next lecture we will directly go into the cache memory architecture, and I will explain what are the different types of cache memory, what is the hardware building block of cache memory, how do we form the address of cache memory, what happens when we have a cache miss, how do you determine cache miss through an algorithm, and so on and so forth. Okay, so we will focus on cache memory in the next lecture. Thank you.